So we are talking about 7.2, which is solving exponential equations and inequalities. We have one little note, and that's all we're really going to have as far as notes. The rest of it will be examples. Our one note is that if b raised to the x power some base, b for base, if b raised to some power equals b raised to some other power, same basis, then it must be true that x equals 1. So as long as you have the same base and some exponents equal to each other, you can ignore the bases. And that leads us directly into example 1, where we are going to solve a couple of problems. The first one is 2 to the x power equals 8 to the third power. Now the idea is to use this idea. The way we're going to use that idea is by changing everything to the same base. What base can everything be in this case? Anybody know? How can I change one or both of these so I'm looking at the same base, the same number here? I can change 8 to a base of 1. That's the idea. You're on the right track. But 2 times 4 doesn't give me a base of 2 or a base of 4. I want to write this as a power, either with a base of 2, or I want to be able to rewrite 2 also. So can I write 8 as a power of 2?
Yeah.
How? What is it?
Wouldn't be 2 squared is 4.
And then times 2 again is, so it's 2 to
the
the
third.
2 to the third, right. So, maybe a little note here. 8 is equal to 2 to the third. So if I can write 8 as 2 to the third, I can rewrite this as 2 raised to the x power equals, and instead of 8, I'm going to write 2 to the third and raise that to the third power. Does everybody see how I did that? 8 is 2 to the third power. So I just substituted 2 to the third power for 8. I have to enclose it in parentheses because I've got exponent and another exponent. But all I did was say, because 8 is 2 to the third power, I can replace this 8 with 2 to the third. Then in my next step, when you raise a power to a power, you multiply the powers, so I get 2 to the 9th. Then I apply this concept here. Now that I've got a base of 2 and a base of 2, I can completely ignore the bases. And I get an answer of x equals 9. Okay? You might think of it as left-hand cancellation. That's acceptable to think of it that way. You can just ignore it. It's like they're not there, because now that you've got the same base, the powers must be equal to each other, because the base with the powers equal.
Alright, so they won't have to be the same.
Right, and that's why we had to do this change right here.
Okay.
Since I can write 8 as a base of 2 with a base of 2, then I can have them both with a base of 2, which allows me to ignore the base.
So you don't need to do that if you can't match it up.
Right, if we can't match it up, we got all sorts of other problems we haven't learned how to do that. We're not there yet, we're getting there. Okay? let's look at B, and B is a little more involved. 9 raised to the 2x minus 1 power is equal to 3 raised to the 6x power. What's the base I can use? Really?
3.
3. Does everybody see that I can use a common base of 3 here? Because I can write 9 as a power of 3.
Yeah.
And then I've already got a 3. So 9 equals 3 to the second, which allows me to then write, instead of 9, write 9 as 3 to the second and raise that to the 2x minus 1 power. Starting to see it now? Good. Then this is multiply this by all of this, which means distribute this. So this becomes 3 raised to the 4x minus 2. It is very easy to make a mistake here and write 4x minus 1. So be careful about that. You have to distribute this 2. And then I've got 3 to the 6x. Left-hand cancellation allows me to ignore the bases and write 4x minus 2 equals 6x. And then I can subtract 4x on both sides. This one negative 2 equals 2x. Divide by 2 on both sides. Then I get negative 1 equals x. And that's all I need. Questions on these? Yes? Okay. So I'll leave B up for right now. And let's go to example 2, which is a fairly interesting example. It's an application example. This does answer the question, where does this show up? Where do we wind up seeing this in real life? And the answer is in the reproduction of unicellular organisms, bacteria, viruses, that sort of thing. Because they keep multiplying and multiplying and multiplying, literally multiplying how many of them there are. And because of that, we're talking about exponential functions, exponential growth. So the second example is that if we start with 7,500 bacteria of some sort, presuming that we count 7,500. And then after 4 hours, we have 23,000 of that same bacteria. So we put it in a petri dish and we let it grow, and it grows to 23,000. The first thing we want to do is write a function to model the situation. Write a function to model the situation. The situation is that we put bacteria into a petri dish. It keeps multiplying and multiplying and multiplying exponentially. And after 4 hours of letting it multiply, we count 23,000. So this is exponential growth. And the way you do these, let's name the function carefully. B of T, bacteria after a certain amount of time in hours. B of T is equal to the initial amount. We always start with the initial amount. What is the initial amount? 7,500 bacteria. The initial amount times some unknown number raised to the T power. The fact that the variable that we will leave as a variable, the variable that's defining the function, is in the exponent, is another indicator that we got an exponential function. So then the question is, what is A? How do we figure that out? Well, in this case, we have another piece of information. We know how many bacteria after 4 hours. So, using this, we can say that there was 23,000 bacteria after 4 hours. So I plug in my number of bacteria and my time, and then I'm going to solve for A. The way I'm going to solve for A, by dividing by 7,500 on both sides. That'll get me A to the 4th here. Did it earlier. If you put this into a calculator, you get somewhere around 3.067. And then you have to get A by itself instead of A to the 4th, so you take the 4th root of A and the 4th root of the other side. We don't have to worry about plus or minus because we know we want a positive number. We know that we want a growth. So when you put this into the calculator, you get somewhere around 1.323 is our A. So then when we want to write our function, we'll write that B of T is equal to 7,500 times 1.323 raised to the T power. So that's our function. This then allows us to predict how many bacteria there would be after any amount of time. For example, in part B, we want to know how many bacteria after 12 hours, right? Yeah, after 12 hours. How many bacteria will we have after 12 hours? Science experiments, a lot of science experiments are done this way. Especially science fair, high school science fair science experiments, where you're going to measure how much bacteria is like on a cell phone. And you can actually go through this process. If you start with and you say, okay, I cleaned the phone and then I looked real carefully in this area and I still had so many bacteria in that area under a microscope or something. I was able to count them, and I waited 6 hours, and I went back and I counted them again, and then I went through this process, and that process allows me to predict how much bacteria would be on presumably almost any part of the phone at any one point. So how many bacteria after 12 hours? Well, that means we're looking for bacteria after 12 hours, which is 7,500 times 1.323 raised to the 12th power. And put that in your calculator. You would say 7,500 times 1.323 raised to the 12th power, which would give you, to me, like, round it to the nearest whole number, 215,665. So in half a day, just half a day, you would go from 7,500 bacteria to over 200,000 bacteria. That's a lot in half a day. That's what bacteria does, it grows fast. Viruses grow real fast. They're some of the fastest growing things out there. There's a virus, I don't remember which one, but there is a virus that doubles every 15 minutes. Which is why when you get sick with that particular virus, you get sick really fast. Okay, so that's example 2. And then we want to talk about compound interest. And the way compound interest works is you get charged a certain amount of money. Let's say you borrow $50. Okay? And they tell you something that sounds good, but is actually really awful, which is same as cash for 3 months. And what they mean is, for 3 months, we're going to compound the interest. If you pay it off in that 3 months, you don't owe us any interest, but after the 3rd month, all the interest that you've accumulated during that 3 months, you get charged. And they don't just say, okay, let's say you had an interest rate of 10%. So that's 0.1. Okay? They don't just charge it to you once. They don't say, okay, you owed us $50, and then after 3 months, 50 times 0.1 is 5, you owe us $55. It's not how it works. Every month, the interest is compounded. So after month 1, you owe $50 plus $50 times 0.1, which is 5, so you owe $55. That's after the first month. After the second month, you owe $55 plus $55 times that 10%. And they keep doing that every month. They get a new amount that you owe, and they just pile it on and recalculate, and pile it on and recalculate, and pile it on and recalculate. So you actually wind up owing a lot more. That's how compound interest works. You can calculate how much is going to be owed or earned from compound interest by this formula. A, capital A, the capital and the lowercase are very important here, equals capital P times 1 plus lowercase r over lowercase n in parentheses, all raised to the lowercase n times t power, lowercase t. Where A is amount after t years, so after a certain number of years. R is interest rate as a decimal. They will almost certainly give it to you as a percentage first, and you'll have to put it as a decimal. And N is number of times compounded per year. And then we got to know economic terms. For instance, if I say annually, compounding how many times a year? Come on. Annually. Once. If I am compounding quarterly, how many times?
Every 3 months.
Yep. How many times is that?
So
4 times. Quarter, 4. Quarter is 1/4. If I am compounding monthly,
Every single month.
12 times.
12 times every month. And then there's a different one, which we're not going to cover in this one just yet. But there's another one. You can compound continuously. You can compound all the time. And that has special properties. We'll get into that in a later section. Okay, so here's our formula. And that leads us into our example 3, which is we invest $2,500, let's say in stocks. It gains 4.2% interest compounded monthly. I'm going to go with monthly because that's what they have in the book. But really, if you're investing in stocks, it's going to be usually compounded quarterly. If you're investing in some sort of savings account, you're not going to get 4%, you're going to get more like 0.4%. So the 4.2% usually is more like a stock investment of some sort. But we're going to say it's compounded monthly. So then we want to know, all we want to know is how much do we have after 15 years? It is, I'm sorry about that. How much do we have after 15 years? So let's set up our problem. We want the amount and our, oh, I'm sorry, I forgot to write one of these. P is the principal, which is, that's the initial amount. So our initial amount is $2,500. And then we've got 1 plus. Our interest rate is 4.2. So that gives us an R of 0.042. Compounded monthly That gives us an n of 12 raised to the 12 times, and we want it for 15 years. 15 years. The way to do this is to calculate the inside of this first, multiply these, then take this total, raise it to this power, then take that total and raise it and multiply it by this number. So when you take your calculator, you do 1 plus and then 0.042 divided by 12. And that gives me 1.0035. And 12 times 15 is 180. So now I can do 1.0035 raised to the 108th power. And then I'll take that answer and multiply by 2,500, giving me an amount of $4,688.87. The more times you compound something, the more money you make, or the more money you owe. Questions about this example? No? Everybody sort of see where this came from? Yes, Natalie?
Where's the restroom?
Yep. One more example and we'll be done. So, it's not going to be too bad. Questions?
Kind of
Yeah.
a general question about
Yeah.
the concept.
Yeah.
So I've been wondering, we're looking at like compound interest and standard interest. Is there a, like, is like compounded, exponential like a thing? Like, I don't know what that would be called. It's not a concept I've actually learned before, but it's one I always wondered about, like how you can have like 2 to the power of 3, that's 2 times 2 times 2. But could you have like 2 times 2, which is 4 times 4, which is 16 times 16, like what's that?
There's
Can you do
no,
that?
I mean, you can do it,
Yeah,
but,
is there any-
but there's no like symbol for it as far as I can think of right now.
I've always like been
um,
surprised that I'm not
There is one if you want to do it just in order. If you wanted to do like 1 times 2 times 3
Yeah.
times 4 times 5, that is a factorial. Which is symbolized with an exclamation point.
I'm talking about like
Yeah,
like squaring something and then squaring that and squaring
right, and I think you could, there is a symbol, I don't know if you guys did
Probably not.
in geometry class, if you guys use the sum notation, where you use capital sigma.
Oh, yeah, we did
No?
that.
Okay. We're going to see a little bit of that in here, so it's okay. But the capital sigma tells you to add things. The capital pi tells you to multiply things in a certain way. So you might be able to do it with this. Okay?
All right. I've just always wondered back.
Yeah.
That's really interesting.
Yeah, it's those two symbols are used like when you have to do weird sort of additions or multiplications. Things that there's no regular operation symbol for. Those are the two symbols that wind up getting used. All right. So one more example, example 4. We are going to solve an inequality, which is going to be extraordinarily just like solving the equations, of course.